Hi everybody. I'm sorry I can't be present in school today. My children's daycare is closed for the day, so I have to be home with my kids. So I figured, instead of just giving you busy work for the entire time, we'll kind of keep this train going, and I'll kind of talk through this. And at the end of the video, if you have questions, reach out to me. I'll try and hop on Zoom. So we're looking at types of graphs and then how we move them. Right, so tied in this domain and range idea we've been talking about, if we have a line, right, there's my line. My domain of every line is negative infinity to infinity. My range of every line is negative infinity to infinity. And in this situation, your y-intercept can be whatever, but if I had just, my bad, I was supposed to graph y equals x. If I have y equals x, which this is, my y-intercept is 0, 0. But every function is going to have the same kind of idea with domain and range, so that's key. So if we have a quadratic, there's my graph of y equals x squared. In these situations, take a moment, make an XY chart and kind of, figure things out. So what's my domain? For every parabola, my domain is all reals. But my range is always going to be, what's in this case, it's 0 up. This number is always going to be the y value of the vertex. Right, even if the parabola is going down. So if I had a parabola here going down, my range here would be negative infinity to negative, what do I got? Negative 5. Oops, I wrote 6. Negative 5. So it's always going to be the y value of the vertex up, the y value of the vertex down. And my y-intercept for the original graph is 0, 0. All right. Y equals the absolute value of x. Got it at 0, 0. Up 1 over 1, up 1 over 1. I got my V shape. Domain and range is very similar to a quadratic. My domain is always all reals, and my range is always either the vertex y value up or the vertex y value down. So here, 0, infinity, because we have vertex y value up. Y-intercept 0, 0. And again, if I had something like this, going down that way, my domain is all reals, and my range would be, in this case, negative infinity, negative 5. All right. I'm going to keep writing y equals, but understand that f of x, that's the same thing as y equals. So I have a graph of a function raised to a third power, y equals x to the third. So I still have my coordinate 0, 0. But now my graph for this has that general shape. And all these parent functions that I'm looking at right now, their general shape stays the same every single time we look at it. And if we have a cubic graph, the domain and range is always all reals. Even if the graph were to move up here, there, that's still all reals. Right? It impacts its x-intercept as y-intercept, but domain and range stays the same every time. Right? Square root graph. Right, so now our domain and range is getting a little bit different here. So we have the domain as 0, infinity, and our range is 0, infinity. And again, what does domain relate to? X values. That 0 is x value of vertex. While our range 0 is the y value of the vertex. And now With a square root graph, we can have a few other options. If I have a negative rad, my parabola would look like that. If I have a positive negative rad graph, my parabola would look like that. So the positive parabola, we have the top of the sideways U. The negative rad, we have the bottom of the sideways U. A positive negative, we have the complete sideways U. And again, my y-intercept, we're still focusing on 0, 0. So if I had my vertex there, my domain would be -7, infinity. My range would be 10, infinity. Talking about x values, talking about y values. All right. 3 more to look at. Rational function graph. I got this, and I got this. So why does this work? Well, to the right of my y-axis, 1 divided by a positive number is always positive, so it's stuck there in that quadrant. To the left of my y-axis, 1 divided by a negative number is always a negative number. So in this situation, no matter how far or how large x gets, 1 divided by a positive is always positive, 1 divided by a negative is always negative. Now what's the issue? X cannot equal 0. Cannot have x equal 0. I can't have 0 in the denominator. But why is the graph firing up to the infinities? Well, let's say 1 divided by 0.5 is 2. 1 divided by 0.25 is 4. 1 divided by 0.1 is 10. The smaller x gets, the larger y gets. That's why it shoots up and up and up and up. 1 divided by -0.01 equals -100. Right? The closer it gets to the y-axis, which is x equals 0, the larger the number is going to get. So how do we write our domain and range? (-infinity, 0, union 0, infinity). (-infinity, 0, union 0, infinity). Is there a y-intercept? Nope, there is none. Obviously, your domain and range is going to change depending on what's up with the equation, but that's in general what we're going to have. Why does it look like this? Well, technically, we have a asymptote on the y-axis, and we have an asymptote on the x-axis. Right, exponential. Now really, I like to think about this as y equals some number to x. Every single number to x is going to have the same general shape. When x equals 0, every number raised to the 0 power equals 1. So I got my dot at 1, 0. And 2 squared, 2 to the third, 2 to the fourth, exponentially increasing. While over here, we're getting smaller and smaller. Now, why does it get smaller and smaller? If I have 2 squared, I got 4. If I have 2 to the fourth, I have 16. But going the reverse way, if I have 2 to the -2, that's 1 over 2 squared, which is 1 over 4, getting smaller. 2 to the -4, 1 over 2 to the fourth, which equals 1 over 16. So as x becomes more and more negative, the number for y gets smaller and smaller and smaller. So what's my domain here? Everything. What's my range? Everything above 0. What's my y-intercept? 0, 1. Right, a log graph. A log graph is an inverse of an exponential graph. So what do we know about inverses? They are a reflection. They flip over the line y equals x. Every point that is on a normal log graph is a flip of the normal exponential graph in this case. So if you have 0, 1, we have 1, 0. If the x-axis is your horizontal asymptote, that means the y-axis is your vertical asymptote. So there's our log graph. And now this is the same general shape of like log of x, log base 2 of x. They all have the same exact thing, same shape to them. What's our domain? Well, if the range up there is 0 infinity, our domain is 0 infinity. If our domain's all reals, our range is all reals. And we don't have a y-intercept. So key thing from these two pages, I want you to be able to look at the equation and have a general understanding of what the graph's going to look like. That's key. Okay, so now, here is our normal y equals x, square root of x graph. Right, so I want to talk about how we modify these equations. So the general form of y equals rad x is y equals a rad x minus h plus k. And this is the exact same thing. Oop, hit a highlighter for some reason. This is the exact same thing as a parabola. And this is the exact same thing as a cubic function. And this is the exact same thing as a third root. And this is the exact same thing as an absolute value. Right? Everything that we're looking at on the previous page basically has this exact same setup. How does HK impact the graph? That's what we're trying to figure out here. So what we got going on is this. If we have our normal graph on the previous problem up top, and we take that graph and throw a +1 on the outside, what's going on? We move the graph up 1. Since the a value in front is 1, we go over 1, up 1 as our second point. Right? All of these have an a value of 1. So all of these have that same idea of up 1 over 1. All right, this one we go down 2 because of the -2. Up 1 over 1 for our second point. There's our rad graph. Right? +1 on the inside. This is a little bit strange. +1 makes you feel like it's going to move to the right, but it actually moves it to the left. Up 1 over 1, because a is 1, there's our graph. The x minus 2 moves it to the right, since a is 1. Up 1 over 1, there's our graph. And now, feel free, take a moment, plug in some values, make sense of this. But the key thing here is that the numbers outside the rad are moving up and down, while the numbers inside the rad are moving it left and right. So, again, outer part of the function, up and down. Inner part of the function, left, right. Now, with the up-down, I feel like it makes sense. Right? You see a +2, it's going up 2. You see a -4, it's going down 4. With the left, right, we basically do the opposite. Right? So if I have x minus 2 plus 6, this graph is going to the right and up 6. Right, now we got some negatives in here. So a negative in front will flip the graph over. Again, since a is 1, down 1 over 1. Stop. All right, part 6, we got it flipped, but what happens with the +1? The +1 moves it to the left 1. We're going underneath, and we still have that up 1 over 1 idea. Right. Down here, the negative's inside. So what we've learned so far is that if something's going on outside the rad, that's impacting the y. Right? So it moves it up, down. Right? If there's a negative in front, it flips it over itself to go up or down. Now, if we have a negative inside, just like when we have the x's inside, the numbers with x inside, that's talking about a left-right movement. This flips this graph to the left. Again, a is 1, so we still have that up 1 over 1 idea, but there's our graph. For 8, this is key. Right, to see the actual movement, we have to have the x and the number in parentheses. So I got rad negative x plus 1 right in there. So the plus 1 moves my graph 1 to the left. The negative flips it to the other side. So I'm going the 1, 1 method, since a is 1, and there's my graph. Right, so if we have a negative on the outside, our negative on the outside, what does that mean? This is called a vertical flip. And we flip over the x-axis. If we have a negative on the inside, it's called a horizontal flip. And we flip over the y-axis. Now, when I talk about axis, I'm talking about the axis that goes through the vertex, right? We'll talk about that in a second. All right, so making a map, right? So I have my original equation. So the first thing I notice is there is a vertical flip due to the negative in front. The second thing I notice is the graph goes up 3. So if I start with my original, my next move is going to be that I have a vertical flip. So now my graph is going down. From there, I got the plus 3. 1, 2, 3. The red is what my graph looks like. So I took my original, I flipped it, and moved it up 3. Always flip before you move. All right, with the second one, do a little work on the inside. Oop. I don't know why it's doing that, but negative. I hit the wrong button. Oop. Alright, so on the inside I got negative, in parentheses, x plus 2 plus 1. So what do I got here? I got a vertical flip. I have a horizontal flip. I go left 2. I go up 1. That's a lot. Alright, so there's my original. I'm flipping this way. Then I'm flipping this way. Alright, so I got my vertical flip, I got my horizontal flip. I actually did it backwards. First I horizontal flipped, then I vertical flipped. Now I'm going to go to left 2. 1, 2. And I'm going to go up 1. Alright, so that second green, that's where my final answer should be. Vertical flip, horizontal flip, up 1, left 2. Alright, so take a moment to erase some of this. There it is. There's my graph. Alright, so this is what I was talking about before with the A value. So when A is 1, I go up 1, over 1. When A is 2, I'm going to go up 2, over 1. So my initial points at the vertex, up 2 over 1, there's my new graph. It's stretched out. This is called a vertical stretch. When A is 3 here, I'm going up 3 over 1. There's my vertex. There's my next point. Even more stretched out. So the larger the number in front, the more your graph's going to be stretched out in these situations. Right, so this is a vertical stretch. And in the situation, if you're looking at the points, right? In the point situation, the y value of the original rad x, they get multiplied by, the A value. And with all of these, I want you to understand, like the left, right, up, down, stretch, flips, in the end, they're just finding points. Worst case scenario, we plug in for x, get y. We plug in for x, we get y. We plug in for x, we get y. Right. Since I'm not in person, I'm just going to skip this for now. I don't want to confuse us. We have not talked about this yet. This is something that we would, in a normal year, we would have already learned. Don't worry about it. I will never quiz you on this right now. This will be for the second semester. Right, and talking about this before, all of these have the exact same idea. A, absolute value of x minus h plus k. A, x minus h squared plus k. A, x minus h to the third plus k. A, not a parenthesis. A third root of x minus h plus k. Even this rational function graph works where it's a over x minus h plus k. Right, so, we'll talk more about that. That goes back to the idea of if we had 2 over x minus 4 plus 10. Our vertical asymptote is now at x equals 4 because we cannot have 4 in our denominator. The 10 moves our horizontal asymptote up 10. So I could say this is y equals 10. Our graph here would look something like that. All right, so, what's the key thing? The key thing with this is it's understanding the left-right movements. Now, I'd focus more on this, this, and this instead of this one. This is not the major one we're going to focus on right now. But normal, moving an absolute value, moving a parabola, moving an x to the third, moving a third root of x, those are what we're going to look at. Alright, so what is this telling me? Negative means vertical flip, left 4. 1, 2, 3, 4. Up, what's my a value? A equals 1, so up 1 over 1, up 1 over 1, and there's my graph. Problem 14. I take out a negative, and I have x minus 4. So this is a horizontal flip. Why can't I write? Come on. I can't write in that spot. Horizontal flip, and we're talking about left 4. Right, so I gotta go left 4. My a value is 1 again. Up 1 over 1. And I'm going that way. All right. Stretch by a half. Right. Oop, not right. Left 5. 1, 2, 3, 4, 5. And now, usually we go up 1 over 1. Since a is a half, we're going over 1. If I make this 1, make this negative 1, we're going up 1, up a half over 1, down a half over 1. Our graph is more compressed. So even though it's called a stretch by a half, the graph is getting kind of smushed. Right, the normal graph here, if we were sketching this out, normal graph would look like up there. And it would be, a little longer looking, while that's a little bit more compressed due to what's happening. What do we got here? Up 5. 1, 2, 3, 4, 5. Up 1 over 1, down 1 over 1. There's my graph. Vertical flip. Right 3. 1, 2, 3. A equals 1. Down 1 over 1. Down 1 over 1. V shape. Vertical flip. Down 3. 1, 2, 3. A equals 1. Down 1 over 1. Down 1 over 1. Here's my absolute value graph. So here we're going left 2, down 3. 1, 2, 1, 2, 3. Since A is 1, up 1 over 1, up 1 over 1, and there's my parabola. Alright, we got a vertical flip, stretch by 3, up 1. So I go up 1, I got a vertical flip, and now since A equals 3, I go down 3 over 1, down 3 over 1. I have a skinnier absolute value due to A being 3. Right, if A was a half, just talking about this now, if A equaled a half, my graph would be wider than normal. If A equaled 1, my graph would just be down 1 over 1, normal. So the larger A gets, right, as A goes up, the graph gets skinnier. If A is between, let's say, between 0 and 1, the graph gets wider. All right. Hopefully that went okay. All right. Hopefully you're able to follow along. You have a practice sheet to wrap up class, and what's left of that's going to be homework. If you have questions, reach out. I hope you're all doing well. I shall see you soon.